Hello, this is the first of four videos for chemistry, paper 2, for you to learn from for your exams. Again, if you want to just listen, you can, but if you want to just stop the video at any point and recreate the mind map, then that may help you to learn. So, if we start off then, this topic is looking at rates of reaction. And the first thing we're going to look at is how you actually calculate a rate of reaction. So there are a couple of ways that we can do this. The first one that we can do is we can use a balance, and we can look at the starting mass in grams and look at the end mass in grams and work out the difference. And the reason we do that is because usually in this reaction a gas has been made and it's gone off into the atmosphere. We can work out the difference, so it tells us the rate of reaction. Another one that you can do is you can use a gas syringe, and you can actually collect the gas that's been released, and you can write down how much gas is made in intervals. So it could be in 10-second intervals or 20-second intervals. But really, the smaller the intervals, the more accurate your results are. Although that does cause problems because it means you have to be looking at the gas syringe all the time and make sure you're as accurate as possible. Now we can use that information to work out the mean rate of a reaction. So the amount of reactant used or the product made divided by the time taken, and that will give us our rate of reaction. Another one you can do is this one here for rate of reaction, and that's 1 divided by the time the solution changes colour. So this one is a colour change, whereas the first one would be more looking at just the rate of reaction with the product being made. Right, this part then is looking at the collision theory, and that's what it's all about. It's all about how much activation energy do those chemicals have to smack into each other, to collide, to have successful collisions, to make a new product. And really, if you've got any questions, and you will have some questions based on this, to do with the collision theory, those are the two terms you must put in your answer, especially if it's a 6-marker. The chemicals have to have enough activation energy to collide and have enough successful collisions to make new products. Absolutely crucial that you put those two terms in. Now, you may be asked to talk about what factors actually increase the rates of reaction. So the first one to look at is temperature. The particles move more quickly, they've got more kinetic energy, and they collide more often when they are heated. And this means you're going to make more products. The second one, which is the actual required practical, is looking at concentration effects on rates of reaction. Now, I think this has got a very good chance of coming up in the exams, because it's the disappearing cross practical, and it's all about adding sodium thiosulfate at different concentrations into a conical flask, and then adding hydrochloric acid. And it's a bit like orange squash. If I've got a little bit of orange squash in the bottom of a glass and I add loads of water, that means it's less concentrated. Whereas if I've got about half squash, half water, more concentrated, and then if I've just got a full glass of squash, that's like really concentrated. And we say that with different acids as well. So 0.5 molar is the equivalent of a small amount of squash and lots of water. 1 molar is more squash and less water, and 2 molar is really strong, more squash and less water. But instead of squash, obviously it's acid particles. So this one, we are changing the concentration of the sodium thiosulfate. So we start off with 10 centimetres cubed of sodium thiosulfate and 40 centimetres cubed of water, and we put that into the conical flask, add 10 centimetres of hydrochloric acid, and then time how long it takes for the cross to disappear. We then change it so that it's 20 of sodium thiosulfate and 30 of water, and then 30 of sodium thiosulfate and 20 of water, 40 and 10, and then 50 and 0. And that is the independent variable. Changing the concentration of sodium thiosulfate is the independent variable. That's the one we're changing. What we're actually measuring, the dependent variable, is the amount of time it takes for the cross to disappear. Now, when it comes to safety for this particular practical, obviously you're dealing with acid, so acid is corrosive, so wearing goggles, but also be aware that they want more detail about safety now, and you should be talking about sulfur dioxide gas can be made if the acid is above 50 degrees, if you're doing this as a temperature reaction, so again, not overheating the acid so you don't produce the gas. So you should have a well ventilated room as well. Surface area. If you look at surface area, this is one that does confuse people quite a lot, because when they look at surface area, they think that the bigger the piece, the more surface area. And in fact, it's the opposite. If I've got one large piece of marble chip, it means all the particles on the outside of the marble chip will react with the acid. And then once they've reacted, then the acid can react with the layer underneath and the layer underneath. If I take that same piece of marble chip and cut it into 4, I know I'm exposing, I've still got my outside surface area, but I'm also exposing inside surface area. So what I've done is I've increased my surface area that is going to react with the acid. So the bigger the piece, the smaller the surface area, and the smaller the pieces, the bigger the surface area. So it's like the opposite if you think about it like that, okay? Now make sure you understand that, because that is one that catches people out. This here is a graph to show you what a rate of reaction would look like. And 9 times out of 10, it is a curve of best fit. And a curve is usually showing you a fast rate of reaction, then it slows down, and then when it levels off at the top, it means that the reaction has stopped. And that's usually because there is a limiting factor. One of the reactants has run out, so you can't make any more. The other thing they might say to you on the exam is, okay, if I plot line A and the reaction is slower, where would the line go? And you might be asked to sketch the line onto the graph. And obviously, because it's lower, it's going to go below line A, but it's going to level out at the same point because you've got the same quantities in the first place. Just check the question first of all. Now, if I want to work out the rate of reaction and use a graph, then it's the change in y divided by the change in x. Now, if it's a straight line of best fit, then that's fairly straightforward, because you can work out the change in y over here divided by the change in x down here. That's straightforward. But they are making the maths skills more difficult now, and they might ask you to work out a curve and look at the rate of reaction. So what you need to do is you need to place a tangent line where it actually mentions in the question. And you need to do that to about 90 degrees of where the curve is. But just try to make sure that the gap on either side is about equal, so that you've got your line in the correct place. And that is for the higher tier only. So draw a tangent line and then do the same again. Work out the difference in y divided by the difference in x. Catalysts. Catalysts are another way to speed up a rate of reaction. The good thing about a catalyst, though, is it's left behind afterwards, so it can react again. Now, if I had to sketch out a reaction using a catalyst, you can see that the line would be further over to the left. It would be a steeper line because the catalyst would make the reaction happen faster. Okay. However, I'm still going to end up with the same amount of products because one of my reactants may have run out. So catalysts speed up a reaction and are left behind to react again. Reversible reactions. This symbol here is showing a reversible reaction. So you've got an arrow going forwards and an arrow going backwards. So if I took chemicals A and B and reacted them together, I'd make C and D. And if I reacted C and D, I could then reverse them back and make into A and B. So here's an example. So if I've got ammonium chloride, you can see that ammonium chloride as a forward reaction makes ammonia and hydrogen chloride. And then as a backward reaction, I can make it back into ammonium chloride. So solid ammonium chloride decomposes, decompose means breaks down, when heated, so that's thermal decomposition, thermal is heat, to produce ammonia and hydrogen chloride gas, which are both colourless. However, if I take that ammonia and react it with hydrogen chloride on this side, gas, I can now produce clouds of white ammonium chloride, so I've gone back to my original reactant. If I'm looking at a closed system, this means that no reactants and no products are removed from the reaction. And this is what we call equilibrium. It means the forward and backward rate is achieved and they are working at about the same level. So that's where we've got the reversible reaction. So going forwards and backwards in a closed system means that the reaction is reversible and equilibrium is achieved. Now if you're doing the foundation paper, you can switch the video off now because the next part is just for the higher tier only. Okay, so if you're carrying on then, so the higher tier only, this is the bit that's a little bit more tricky. And I've tried to display this in a way that hopefully will help you to remember it. And that is Le Chatelier's principle, which states that if a system is in equilibrium is subjected to a change in conditions, then the system shifts to resist the change. So for instance, exothermic reaction here, if the temperature increases, the yield decreases. If the temperature is lowered, the yield increases. So you can see that's the opposite. So if it's exothermic, temperature goes up, yield goes down. Temperature goes down, yield goes up. Okay, so that's the first one. The next one though, endothermic, if you look at an endothermic reaction, if the temperature goes up, the yield goes up, the yield increases, and if the temperature goes down, the yield goes down. So exothermic, temperature up, yield down, temperature down, yield up, the opposites, whereas endothermic, they are both the same. Temperature up, the yield goes up. Now if I look at gases, if I've got gases that are under more pressure, then they tend to favour the less gas reaction, where there's less gas reaction in the first place. Whereas if I've got less pressure, it tends to favour more gas and with the reaction. So again, sort of the opposites again. And then the last one that you need to know is about concentration. Well, if you think about it, if I've got, let's just say if I've got nitrogen and hydrogen and I'm reacting them together to make ammonia, and that's the Haber process, so it's a forward reaction and then a backward reaction. If I added more nitrogen and more hydrogen, then obviously the shift is going to go to the right to make more products because I've added more reactants. So it's going to shift to the right and then equilibrium will then be reached again. And then it's the opposite. If I add more products, then obviously the shift is going to go more towards the reactants. Now that is one that is quite, it's trying to remember whether they're positives, whether they're going up or whether they're going down. So it's worth making a little list so that you've got your exothermic, endothermic, what happens in a gas and what happens in the concentration. If you want to watch the video again, or if you want to make yourself a mind map or ask yourself questions, then please do, and then move on to video number 2.